talk about an off-grid PV system for a commercial ship ranch in Australia. The location is Commonwealth Hill Station, Muglathing, South Australia. We are members of Group 2. I am Raj Patel and other presenters are Anjum, Sandip, Sherchan and Santosh Giri. Our instructor is Professor Walter Thomas. This will be our agenda for today's presentation. First of all, I will discuss background information including site plan and available energy resources. Then I will focus on miscellaneous electrical appliances and the load modeling. Further, Santosh will present you HVAC load, water heating load, lighting load and farming load. Then Sandip will discuss system design using hand calculation as well as Homer Pro analysis. And finally, Sana will conclude with the economic analysis of the system. Background information. Location: Commonwealth Hill, Muglathing, South Australia, 69 miles west of the Stuart Highway. Coordinates are these, and the whole ship station is managed by Jambak Pestra. They are the largest landowners in Australia and they are the biggest wool producer in the country. They own over 0.3 million head of sheep and 80,000 head of cattle spread over 19,000 square mile in the Australia. And if I talk about this station, the available land area is around 3861 square mile and the annual livestock is 30,000 merino sheep. And this is the bird eye view of the site, and there are some buildings. This is the satellite image, and as we can see there are some buildings spread over the station, and we have designed a site layout based on that. So there are 3 big buildings for farming purpose, which are sheep shearing building, sheep shelter building and food storage unit for sheep respectively, and the other small 3 utility buildings are employee building 1 and 2 and a common building. Floor plan for utility buildings. A common building will have a TV room, an office, kitchen, dining area, laundry storage area, as well as toilets and bathrooms. Initially, we thought of having an electrical room separate behind this common building, but then found that laundry storage area was large enough, so we have kept 10 by 10 room for battery inverter placement, and this small room has 2 windows so that battery heat can be easily dissipated through natural ventilation. Now there are 8 employees, so 8 bedrooms are designed in a manner that each employee gets a separate entry door and window. We have proposed to club 4 bedrooms as an employee building so that conditioned wall area to the ambient temperature is reduced, which will help in reduction of overall cooling load. And as we can see, these 2 walls now are adiabatic, so rather than having 8 separate rooms, this setup will help in reduction of overall cooling requirement. And there are no windows kept in north facing walls, so that heat gain is reduced because the site is in southern hemisphere, although there is one in this toilet which is required just for ventilation. This is an image showing 3D front view of utility buildings, which we have just put from our SketchUp 3D model. This is a 3D rear view of utility buildings, and diesel generator set is decided to put just behind this battery inverter room so that wiring cost is reduced, and AC panel and switches will be carried by this box. And as I discussed, this small room has 2 windows, and we have also decided to put all our ground mounted panels at 30-degree tilt angle and 20-degree azimuth, and we will put those panels just behind this utility building. These graphics represent average hourly temperature throughout the year. Vertical axis represents the time of a day, and if I divide these temperature regions in 4 portions, those will be comfortable, warm, cool and cold, and the temperature ranges from 55 degree Fahrenheit to 95 degree Fahrenheit. Starting from mid-November to the end of March, during day hours, temperature remains warmer. Nowadays, it mostly remains in comfort zone during the day, which is 70 degree Fahrenheit to 80 degree Fahrenheit, and during winter months, in the night hours, temperature remains in closed cold region, which is somewhere around 60 to 65 degree Fahrenheit. And this shading line is to show daylight hours. So during summer, sometimes daylight hours are more than 13 hours. We can see it is around 7 a.m. to 9 p.m. in December. Available energy resources, solar power. So average GHI is 4.6 kWh per meter square on daily basis, while wind speed of an average 7 meter per second is available at 50 meter elevation, while diesel price is 3.75 US dollar per gallon in April 2021. This graph shows variation in GHI, global horizontal solar irradiation, all over the year, and we can see in winter months it ranges from 1.6 to 2.6 kWh per meter square on daily basis, while it is increased to 6 and ranges between 6 to 7.2 during summer months. Now, these two line charts are indicating monthly average wind velocity at 50 meter and 10 meter elevation. So, wind profile is not that bad. On an average, wind velocity remains between 6 to 7.3 meter per second at 50 meter elevation. This is the trend showing average diesel price in South Australia. Due to increment in global crude oil prices, diesel price has risen up to 3.75 US dollar per gallon currently in South Australia. These are the miscellaneous electrical appliances. We have divided those appliances as per the utility area, and most of them are in kitchen: coffee maker, refrigerator, toaster, microwave oven, dishwasher. And if I talk about laundry, we have assumed one load per day, as there are 8 employees, but we have only one washing machine and a dryer. So each employee gets it done after 7 days. So that would be like one employee can only wash and dry his clothes on a particular day. And if I just sum up the energy consumed by these all MELs, it comes around 21.35 kWh per day, and most of them will be consumed by dryer and refrigerator, which will be more than 60%, and the maximum connected load on a particular day would not increase 10.475 kW if all these are running simultaneously. Now, Santosh will go over lighting, HVAC, water heating, and farming load. Thank you.
Hello, I'm Santosh, and now I'm going to talk about the remaining electrical load in the SIP branch. To calculate the lighting load, we use this the Bond.com online tool where we can give the size of the building or bedrooms, kitchen, including their height, and that will give us the number of lamps with the wattage power to illuminate that building with the desired intensity of light. So from that online tool, we got the number of lamps as shown in this table here, and then the hours of operation we assume is shown in this column, and total amount of electrical power needed to run the employee building is 1340 watt hour. And for the farming building illumination, we have three big farming buildings, each of 6,000 square feet. And from the same online tool, we got a 43 numbers of electrical bulb, each of 18 watts. So to illuminate those three buildings, we need 2322 wattage of power. And as we assume 11 hours as an hours of operation in a single day, that will consume 2500. I mean 25.542 kilowatt hour of energy. And for the street lighting, there are six numbers of LED lights, each of 50 watt running for 11 hours. That will consume 3300 watt hour of energy. So in this way, the total amount of electrical load will be 30.182 kilowatt hour in a single day. For the farming load, we have to use different kind of farming equipments, such as seed clipper, Mac baler, a submersible pump to extract the water from the ground, to pump the water. So the amount of water we're going to need, we calculate in this way that we assume that 3,000 numbers of sheep will be there in every single day to drink water. And one sheep needs 3.7 gallons of water, and 20 gallons of water is needed for one employee. Uh, so the total amount of water needed comes out to be 11,269 gallons every single day. So we use 2 horsepower submersible pump, which can discharge the water at 35 gallons of water every single minute. So in this way, we have to run this submersible pump for 5.5 hours every single day to meet the water demand. And all the electrical equipment, their power rating and their operational days is shown here, which shows that 29,875 watt hour of energy will be needed to run the farming load. So this is the data sheet for the submersible pump. For the hot water load, we are using solar heating system from the EcoSmart solar water heater with electric boosted 400 liter. That means this solar heating system can be run with the electric boosted as well. So in the winter time, the HVAC load will be reduced. So that HVAC load can be shifted to use the to heat the water in the winter time to make the hot water. So this electric water heating system can hold 105 gallons of hot water at fairly high temperature of 160 degrees. So this is the capacity of 3.6 kilowatt. While talking about the HVAC load, so this table shows the different kind of materials that are using in the different parts of the building, wall, ceiling, floor, and door, and their R values and U values is shown here. And this is the table showing the U values for the employees building. We have 2 employees building for the residential purposes. And for the TV room and office, this is the area of the windows, door, walls shown here, and this is the UA values for that. And for the calculation, we use the natural air leakage in the standard ratio of 0.2, and ground temperature was 50 degrees Fahrenheit, and highest ambient temperature is 114 degrees Fahrenheit. So to calculate the HVAC load, we assume 114 degrees at the highest temperature in a single day. In this way, we calculated how much energy is needed to cool down the building to 75 degrees. So that comes to be 4,000 BTU of energy need to be extracted from the building, which is equivalent to 1.2 kilowatt hour in 1 hour to keep the building in 75 degrees at the hottest time of 114 degrees Fahrenheit. So this table shows the amount of energy that we're going to need in a 24-hour time span for one building, one employee building, which shows 10 kilowatt hour of energy that is needed. In this way, we calculate the HVAC load. So here we can see for the building 1 and building 2, they are exact same size, and we are using AC system for that. And we need a 10 kilowatt hour energy to keep that building in 75 degrees Fahrenheit at the hot summer time. So every single room will use 500 watts power of AC system, and the hours of operation is calculated in that way that the AC system is automatic. That means when the temperature will go up, then 75 degrees, the AC system will be kick on automatically, and when the temperature go down, this will kick off. That means to keep the building at that set point temperature, the AC system will be periodically turn on and turn off. That means that is equivalent to running that AC system 5 hours a day. So that's how we calculated this hours of operation. And for the office TV room, we are using the same kind of AC system that will run for 4 hours, and that is equivalent to 2 kilowatt hour of energy needed in the hot time. And for the kitchen, storage, laundry, steering building, and these buildings we are using the industrial fans. And these are the hours of operation, and their power rating is given here. That means for the HVAC system, we're going to need 39.18 kilowatt hour of energy in a hot summer day. So these are the pictures showing the AC system and industrial fan that we're going to install. So in this way, the total load we calculated in the peak time came out to be 122.578 kilowatt hour, including lighting load, HVAC, farming load, and all the electric appliances. When we calculated this load, we know that HVAC load will not run every single day in the year. That will run only for 242 days in a year. And but lighting load will run for 365 days. In the same way, clipper boiler will be run only for 30 days when the farming work will be there. And other loads will be run almost every single day in the year. So in this way, we calculated the total amount of energy that we're going to need over 1 year, which came to be 33,183.24 kilowatt hour. So this is the total amount of energy that we're going to need over 1 year period. So when you calculated that period or that energy is in average per day, that came to be 90.91 kilowatt hour. So our peak energy in a day is 122.578 kilowatt hour, and average energy per day is 90.91 kilowatt hour. So this is our load calculation. For the remaining slides, I would like to request Sandip to proceed. Thank you.
Thank you, Santosh. Hi, everyone. My name is Sandip Sherchan, and I'm going to present you the system design of this ship range. So we got the average load of 90.91 kilowatt hour AC from the load calculation, and we chose the inverter of efficiency 96%, which gives the DC energy of 94.69 kilowatt hour. This much of energy must be supplied from the battery. So we chose the battery date of discharge 50% and the round trip efficiency of the battery 80%, which gives the 211.74 kilowatt hour of capacity for 1 day. As the South Australia is pretty sunny most of the time, we get 423.48 kilowatt hour of battery capacity for 2 days of autonomy. So we chose the charge controller with 95% efficiency so that the panel must supply the 99.67 kilowatt of DC energy. The maximum production at this location is for tilt angle of 30 degree and azimuth angle of 20 degree from the PVWAS online software. And the peak sun hour for these angles at the lowest radiation month in July is 4.09 hours, which gives the total capacity of panels required to be at least 27.24 kilowatt. We have the 130 kilowatt diesel generator, which supplies the load when the state of the charge of battery drops to 50%. Now move on to why we choose these system components in our system. Let's start with the battery. And the battery we choose is a Mighty Max battery having the capacity of 12 volt 250 ampere hour for 20 hours. This battery is maintenance free, and so that there is no need of watering. It can go up to 700 cycle for 50% date of discharge, which is at least last for 2 years. The main reason to select this battery is the cost of the battery, which is just $145.79 per kilowatt hour, which is normally around $300 per kilowatt hour for AGM batteries. And inverter we chose is a 2 into 15 kilowatt Vectron Quad-Go inverter charger. The reason to select this inverter is its charger also, and it senses the state of the charge of the battery. And when battery state of charge drop to 50%, it automatically start the generator and simultaneously supply the load and charge the battery. It always fulfill the load demand first and charge the battery with the rest of the power from the generator. The PV module we choose is Canadian Solar CS3U 355 watt solar panel. This panel has a 17.89 efficiency and the greater temperature range, operating range, and the cost is also a factor to choose this panel, which is just 155.034 per piece from the online vendors. The charge controller we choose for the system is Schneider Electric 6 kilowatt MPPT charge controller. As we need the at least 27 kilowatt of power from the solar panel, our focus on the charge controller is to select the higher capacity so we can compromise more panels to reduce the cost of the system. And we found this controller which has 6 kilowatt of rating and MPPT range of 550 volt. Now focus on the number of components. So our total load is about 31 kilowatt, which is not peak. So we select the 2 inverter of 15 kilowatt each. And for battery, our requirement was 423.48 ampere hour. And the battery we selected was 12 volt 250 ampere hour. But the voltage rating of inverter is 48 volt. So we have to series 4 batteries to make the 48 volt and to cover 423.48 ampere hour. We have to make 36 string. So now in total, the capacity of battery is 432 kilowatt hour and the number of batteries 144. Now the number of solar panel for our design, we need at least 27.24 24 kilowatt hour of solar panel rating, and our module rating is 355 watt. So we made 8x2 string for charge controller, because the charge controller voltage limit is 550 volt and the power limit is 6 kilowatt. So in total, we have 80 panels equal to the 28.4 kilowatt of rating and 5 charge controller, 16 for charge controller in 8x2 combination for controller. This is the single line diagram of the system. So we have 10 string of 80 panels of rating 355 watt for each model. And then this 10 string goes to the 5 combiner box, 2 string per combiner box. And then the DC energy goes to the 6 kilowatt Schneider MPPT charge controller and goes to the battery storage system of 4x36 string of 12 volt 250 ampere hour Mighty Max battery. Then this DC energy is converted into AC energy by 2 into 15 kilowatt of 2 quadrigo inverter, then supplied to the load. So we have also a 30 kilowatt of diesel generator, and it operates if the battery state of charge drops to the 50%. And as I talked already, the inverter automatically start the generator and simultaneously supply the load and charge the battery, and this inverter gives the priority to the load first. Now move on to the Homer system design for the load of 90.90 kilowatt. The commercial system design in the Homer Pro gave the optimized PV system capacity of 40.3 kilowatt, a battery capacity of 51.6 kilowatt, capacity of 2 batteries, and the inverter capacity of 14.9 kilowatt, and the diesel generator capacity of 30 kilowatt. This is the screenshot of the electrical production from the optimized system of Homer Pro, and we can see the diesel generator is required during the summer month. For example, January, February, March, November, and December, when there is a requirement of to run the AC and the farming load. The renewable penetration is 97.9%, and there is excess PV production of 48,232 kilowatt hour. This is the screenshot of the batteries summary from the Homer Pro, and it shows that the battery is mostly used in the summer month, January, February, March, and then November, and drop down to the 50% of the state of charge sometimes. And the optimized battery system from the Homer Pro has 13.6 hours of autonomy, and the expected life is 7.47 years. So comparing the design wise, we got 28.4 kilowatt of PV system in hand calculation, but the Homer Pro has 40.3 kilowatt of system. This might be due to the Homer Pro has better data of solar radiation. The storage system in the manual calculation is 430 kilowatt, 32 kilowatt hour, but the Homer Pro system has a 103.2 kilowatt hour. This is due to the 2 days of autonomy we have put in our hand calculation. And furthermore, the inverter in the hand calculation is double the size of Homer Pro calculation, because the inverter in the hand calculation can cover 95% of the load at a time. So for the financial calculation, I would like request to Sana.
Hi, I'm Sana Anjum, and I will be covering financial analysis. According to South Australia Sheep Industry Blueprint Study, the sheep, wool, and lamb industry generates about $1.48 billion revenue annually, and Commonwealth Hill Station also contributes in this revenue. The Commonwealth Hill Station is operated by Jumper Producers, which is one of the largest sheep and cattle producers in Australia. There is a need of an off-grid PV system for Commonwealth Hill Station because of the current electricity rate, which is 0.26 per kilowatt hour, and this is the highest rate in Australia for the time being. Moreover, the supply of electricity is unreliable from the grid due to long transmission lines. Therefore, for less expensive and reliable electricity, the station requires an off-grid PV system. In capital cost, we have calculated total cost of the PV system by including individual cost of the components. The main component of the system as shown in the table are PV modules, batteries, solar charge controllers, inverters, combiner boxes, diesel generator, soft cost for solar and diesel generator are also taken under consideration. The table also displays per unit cost, quantity, and total cost of a component. For example, for the PV Canadian solar panels, the per unit cost is around $155, and with a quantity of 80 modules and the total component cost is coming up to be $12,402. Similarly, the total cost for every component is calculated, and the total cost of the system is coming up to be $170,662. Incentives and calculations. Talking about incentives, the system is applicable for two incentives: the Small Scale Technology Certificate Incentive and Home Battery Scheme Incentive. The Small Scale Technology Certificate Incentive is calculated based on location, installation date, and the potential amount of electricity generated over the course of time. There is an online rebate calculator which gives the rebate amount based on size, location, and year of installation. And from that calculator, the rebate for the system is $17,440 with input of 28.4 kilowatt capacity. Whereas through Home Battery Scheme Incentive, the system can also get maximum subsidy of $3,000, which is given per battery installation. Now talking about financial calculation. For financial calculation, a spreadsheet model is used to calculate simple payback, cash flow, and NPC. The table shows the input for the calculation, and the inflation rate in Australia for 2021 is 1.34%, which is we have taken for this calculation. The operational and maintenance cost of the solar panels is 1% of the initial cost annually. The inverter and controller have an operating cost of 1.5% of initial amount, and the replacement cost of the inverter is 50% of the initial cost. Battery operational cost is assumed to be 1% of the capital cost, and replacement cost is assumed to be 60% of the capital cost. Generator maintenance cost is $300 per year, and replacement is 90% of the capital cost. The interest rate is 4.99% over 7 years, also known as green loan. The tax rate is 45%. The discount rate is 3.1%. The system got a simple payback of 17.41 year with a negative cash flow and a negative NPC. Comparison and conclusion. On comparing the spreadsheet results with the Home Pro, we can see that Home Pro has 1.6 years of simple payback and a positive NPC. Moreover, the system from Home Pro has fewer components, which will lower the upfront cost for the branch owner. Not only this, with the Home Pro PV system can give the access energy of 48,232 kilowatt hour annually, which can be used for different purpose in future. Therefore, we can say, or we can conclude by saying that the design for off-grid PV system obtained from Home Pro is recommended for Commonwealth Hill Station. And that will be all from our group. Thank you so much.